Okay, this is the answer key to practice 17D. And get a pop-up ad. So let's take a look at getting some data input into our calculator. So I'm going to clear the memory. And we're going to hit 4. And that will clear all of our lists. Okay, so now that we have that all ready to go, here we go. It says, number 1, a certain reaction has the following general form. And it gives us some data, and it asks for 3 things. It says, state the differentiated rate law, the integrated rate law, and the value in units of the rate constant, integrated rate constant K. Okay, so let's get this data into our calculator and see what it looks like. So let's do our stats list, and we'll enter our time in L1. I'm not worried about the decimals. And we'll enter in L2 our concentration, 0.1, 0.017, 0.009, 0.0062, and 0.0047. And it's always a good idea to double check to make sure that you entered it correctly. And I see right off the bat that I did not enter this one correctly. It should be 0.017. And that is better. So let's go up to our stat plot, and we're going to turn everything off. So let's make sure that plot 3 is off. We'll go up to plot 1 because this one is currently set up to graph L1 versus L2. We'll make sure that it's on, and we'll hit graph, and we're going to zoom to the data. Very clearly not a straight line, and as a matter of fact, that's a big jump. I'm going to make sure that I entered that data correctly. Yeah, and it looks good to me. 0.1, 0.017, 0.009. That's how the data looks, and sometimes data is screwy. So let's go to L3, and we'll instruct the calculator to take the natural log of everything that's in L2. And let's graph this. So we're going to go up here. Let's turn this one off, and let's turn plot 2, which is already set up to graph L1 versus L3, on, and we'll graph it, and we'll zoom to the data. And that is clearly also not a straight line, so we're going to go one more and tell the calculator to take the inverse of everything that's in L2. So we're going to tell the calculator to take L2 and invert it. That looks good to me. Let's see if we've got a plot ready to go for this one. Number 3 is ready to go. So let's turn plot 2 off, and we'll turn plot 3 on. We'll graph and zoom to the data. And that is a straight line. That means that this is clearly second order. So when it says differentiated rate law, that's going to be this one. Rate is equal to K times A raised to the second power. And the integrated rate law will look like this. The concentration of A is equal to KT plus the inverse of A at time 0. We want the value in units of the rate constant K. And there's a faster way to get the value, but the units are fairly involved. Unless you memorize them. I happen to know that the units for a second order reaction are always liters over mole second. And if you wanted to get the value in units of the rate constant K very quickly, you could just go to your calculator, go to your statistics, tell it to run a calculation of linear regression on the list of L1 versus L3, and that would give you the value in units of the rate constant K without a whole lot of fuss. And I get a value of 10.16. And I'll put that right here. Now, if you don't want to do it that way, you could do it by picking a time and a concentration and plugging everything in. And so doing that, K would be equal to 1 over A minus 1 over the initial concentration, which is 0.1 moles per liter. And dividing that by time, which we picked was 5 seconds. So we'll enter the concentration at 5 seconds of 0.017 moles per liter. Now when you do this, moles per liter are going to invert. You'll get liters over moles and of course 5 seconds. So let's go back to our calculator. My battery is running low. And we'll instruct our calculator to take 0.017. We'll invert that. We'll subtract from that 0.1, and we'll invert that. I'm going to get rid of that, and then I'm going to divide this whole thing by 5. We should get something that, if it is not exactly equal to our slope, should be close. 9.77. So either one of these is valid. I would take either one because you got 1 by using the slope of the line, and you got 1 by solving. So either one of these would do the trick. Okay, now a good idea to keep all this stuff straight is to take this guy, this list of equations, this thing. Let's copy this and bring this here so that we have it. Because it's a good idea to reference these if you don't have them all committed to memory. I don't quite. So, if we are looking for the half-life of a second order equation, the half-life equation looks like this. So, what's the half-life? T 1/2 is equal to 1 over the rate constant K times the concentration of A at time 0. Well, you know both of these. You're going to get something slightly different depending on what rate constant you use, and I am totally cool with that. But you can at least get an idea of the value for half-life, and we don't have a whole lot of time before we get to 0.05. I mean, the first interval is 5 seconds. I'm going to look for an answer for my half-life somewhere in between 0 and 5. Again, if you get a different rate constant, you're going to get a slightly different answer, and it doesn't matter. We'll use this one, and then if you're curious, we'll use the other one, and we'll see if we get something close. So we're going to take 1. We've got a rate constant, 10.16. Remember the unit liters over mole seconds. And we've got a concentration at time 0 of 0.1 moles over liters. Now look what it does to the units. Moles cancel, liters cancel. Gives us our answer in seconds. Remember, we are expecting a time of less than 5 seconds. So what I'm going to do is I'm going to plug this stuff in the bottom and then invert it. So we're going to say 10.16 times 0.1, which I don't really need a calculator for that. And I'm going to invert this by taking x to the -1. And that fits exactly with what I was expecting. Less than 5 seconds. We'll call that, I mean, if you want to say 0.984 seconds, you can. That's close enough to 1. If you want to try it with the other value for the rate constant K, you'll get an answer that's very similar. We'll say 9.77 times 0.1, and we'll invert this answer. We should get something pretty close. 1.02 seconds. Again, approximates to 1 second. All right, last one. What is the concentration of A going to be at 35 seconds? So if we know that the rate law for this equation is the second order version, then our equation to set up to find concentration is going to look just like this. We're going to plug everything in. So what's the concentration of A at 35 seconds? We have a K, and feel free to use whichever one you want. I'm going to stick with this one, 10.16. The units are, of course, liters over moles seconds, times 35 seconds plus the inverse of the concentration at time 0. Okay? Now when you do this, seconds is going to cancel out. You have liters over moles in this one, moles over liters in the denominator, which are going to invert. You'll see what I'm talking about in a little bit. So let's take our calculator and we'll say 10.16 times 35. This is going to be 355.6. We're going to add to this the inverse of 0.1, which you should know is 10, but we're going to do it by the book. 365.6, and that is the inverse of our concentration at 35 seconds. So I'm going to take this answer and invert it back, and this will give me my concentration at 35 seconds. If you want to estimate it, it's going to be somewhere less than 0.0047. If it doesn't look like less than 0.0047, yeah, screwed up. 0.0027, and that looks fine to me. So our concentration, 35 seconds, 0.0027, and the units are moles per liter. Okay. All right, let's do the same thing here with number 2. So we want to find the order. It asks, state the differentiated rate law, integrated rate law, and the value in units of the integrated rate constant K. So we should be pretty familiar with this stuff by now. Let's go to our calculator and let's clear the memory. And okay, so we've got clear all lists, we've cleared the memory, and we can go to our statistics and enter. So let's get our time, 0, 10, 20, 30, 40, 50, 60, 70, 80. Let's get our concentration. And you know what's interesting about this concentration stuff is that if I'm looking, it seems to be dropping by about the same amount every time. It seems to be dropping by about 50, 0.005. If you look at this, if you were to subtract each of these from the next one, you get a pretty consistent value. I'm going to estimate that this is a zero order reaction. Let's see how close I can get by just eyeballing it. 0.0447, 0.0394, 0.0341, 0.0288, 0.0235, 0.0182. Whoops. Didn't want that. 0.0182. My calculator is not happy with me. Let's edit. There we go. 0.0182, 0.0129, 0.0076, and 0.0023. Looks like we're in good shape. Let's graph this stuff and see what happens. So let's turn plot 3 off. Let's turn plot 1 on because it's already set up as L1 versus L2. Graph, zoom 9. I predicted a zero order reaction. Boom!